In this little section, what we're going to do is have a look at the preparation of amines, so how you can make amines. So first of all, we need to consider the different types of amines and make sure we totally understand the types of amines so that we understand the different ways to make them. So we're just going to have a look at what we mean by an aromatic amine. So aromatic amines are amines that contain a benzene ring attached directly to the amine there, so that N is attached directly onto our benzene ring. This particular structure here is called phenylamine. So this is the phenyl group. Benzene is called phenyl as a substituent attached onto an amine. Some people might refer to this as aminobenzene. So there's an amino group on a benzene, but the IUPAC name is phenylamine. So just to be aware, not all amines with a benzene ring are aromatic amines. The amine group must be directly attached to the benzene ring for it to be an aromatic amine. So phenyl, that's this bit, on a methylamine is not an aromatic amine, as the amine group is not directly attached to the benzene ring. This would class as an aliphatic amine, like a chain amine, so the amines on a chain, and we'll look at their preparation a bit later. So have a look at these three structures and decide for yourself whether you think they are aromatic or aliphatic amines. So here we go, let's have a look at the answer. So this first one here, is the amine directly attached to the benzene ring? Yes, therefore this one is an aromatic amine. Let's look at this one. Got the amine group here, is it directly on the benzene ring? No, therefore it's aliphatic. And again, here's the N of the amine. This is a tertiary amine, whereas these two were primary. Is the N directly attached to the benzene ring? No, therefore it's an aliphatic amine. So how do we make aromatic amines? So first thing we have to know is that the type of reaction is called a reduction. We're swapping out oxygens for hydrogens. We're increasing the number of bonds to hydrogen, reducing the number of bonds to oxygen. We're changing an NO2, a nitro group on a benzene, into an NH2, an amine group on a benzene. So that's how we're going to make them. It's going to be a reduction reaction. So we need to consider how we're going to do that. So if we're asked for the reagents and conditions of this reaction, we need to know that the reagents are tin and concentrated hydrochloric acid. Both of those things are the reagents. And that's a reducing mixture. Just like we might say acidified potassium dichromate, and that's an oxidizing mixture. Tin and concentrated HCl, all of that is the reagents that are the reducing mixture. And the conditions are reflux. And remember, this is how we set up reflux, where we're going to heat it without loss due to evaporation. So what would we write for our equation? Well, tin and concentrated HCl, it's a lot to balance. And so we're in our organic chemistry reactions, we're allowed to use H in square brackets to represent reducing, whereas we used O in square brackets for oxidizing, because we were adding oxygens. Here we're adding hydrogens, so we're going to use H in square brackets. So the square brackets tell us it's a reducing mixture as opposed to it being actual hydrogen. So we've got H in square brackets, and in order to balance this equation, because the two oxygens have to come off, we need to make two waters. And two waters already contain 4 hydrogens, and then we've got 2 more, so in total we've got 6 hydrogens we need to be giving to the starting material in order to create these products, and therefore 6 hydrogens means 6 lots of the reducing mixture. Okay, so let's just have a look at these two, and in these two the only difference is we've got 2 nitro groups here, so we're going to need to reduce both of those. And so we've got 4 oxygens, that will make 4 waters, and if we add up the hydrogens on this side now, we see that we're going to have 12 H's in square brackets. So by doubling the number of nitro groups, we've had to double the number of reducing mixtures and double the number of waters. And if there were 3, you can see how that would play out if there were 3. Okay, so let's move on and have a look at these aliphatic amines, amines that are on chains rather than on benzene rings. And we've got 2 different methods to think about. The first method is where we just take our halogenoalkane, and we've learnt about this in the halogenoalkanes pack, and we swap it out for an amine. We use ammonia as our reagent, and it's a nucleophilic substitution. So here's an example: 2-chlorobutane becomes this amine, and although we might want to call this 2-aminobutane, which would be nice and easy, 2-chlorobutane, 2-aminobutane, its actual IUPAC name is counting from the amine 1, 2, 3, propylamine with a methyl group on number 1, 1-methyl propylamine. That would be its IUPAC name. So we're just swapping out a Cl for an NH2 using ammonia. So our reagents are ammonia, but our conditions are, we say, excess ammonia, so we need to have plenty of ammonia, and that's going to become really important later in this pack, why we use excess ammonia. In ethanol, that's our solvent, so not in water, in ethanol, and we're going to warm it up. So we're going to warm excess ammonia in ethanol. Ethanol is a solvent, ammonia is the reagent. Excess ammonia is also an additional condition. Right. When we write the equation for this is one of these little twiddly bits that just there to catch us out. We're going to need a 2 in front of the ammonia. And if I take it down to the bottom, we can see why. So the first thing that happens is ammonia does a nucleophilic substitution, a swapping reaction with the Cl, and we get NH2 on here. And so we're getting a H and a Cl here as a product. Now HCl is an acid and ammonia is a base. And if those two things are in a beaker together, because we've got excess ammonia in the beaker, it's for reasons we're going to learn about later, it's to avoid something called further substitution. Got excess ammonia in the beaker, then ammonia and HCl are going to react to make a salt. If we join these two equations together, the HCl will cancel out and we'll end up with our halogenoalkane, and 2 ammonias make our amine and an ammonium chloride salt. And that's what we've got at the top. So we just need to remember that there's 2 and we make a salt. If we just remind ourselves about the mechanism for this reaction, when we're doing the mechanism, we are actually just describing step 1. We are just describing the nucleophilic substitution. We do not need to describe the acid-base reaction that also happens when we're asked for a mechanism. So in goes the lone pair with the ammonia, in goes the nucleophile, and out comes the bromide ion. There it is. And then in the next step, a proton is released, H falls off as H+. You can, and you will see it sometimes, see an ammonia coming in and grabbing this, but you don't need to do that. If it helps you to remember the 2 ammonias in the equation, then by all means do it, but it is just an extra curly arrow and you don't need it for the exam. So in goes the ammonia and out comes the Br, and then off falls our little hydrogen to give us our amine. What's our second method then? Well, our second method is when we want to increase the length of the carbon chain. So say we start with prop, we're going to end with bute. We're getting longer, and it's just a 2-step synthesis. So the exam board often will try this one out on you because they'll see if you will fall into the trap and try to just use ammonia directly and end up with the wrong product. We're going to take our halogenoalkane and this time swap it for a cyanide, and then we're going to take the cyanide and turn it into our amine. So you'll notice if I give you this example, 1-chloropropane suddenly became butane nitrile because we added a C, and then that became butylamine when we turned it from a nitrile into an amine. So we've got 2 steps. Step 1 is our nucleophilic substitution from halogenoalkanes. We're going to use KCN that we're going to warm in ethanol. And step 2, which is the main step in making the amine, we're going to reduce the nitrile into an amine. And our reagent for that is just hydrogen, the element. And we're going to have a nickel catalyst and a high temperature and pressure. Hydrogen's a gas, to force it in there at high temperature and pressure, nickel catalyst. So step 1, we swap the CN for the Cl. So there's our nucleophilic substitution. And step 2, we're going to reduce the CN into an amine. Now when we do this, we don't need to use H in square brackets, although if you did use 4H in square brackets, you would get it marked correct. We can just use 2 H2s because our reagent was hydrogen. It's not that difficult to write it down and balance it in an equation. So we just use 2 H2s. We're going to put 2 onto the C and 2 onto the N. So in my skeletal formula, the CH2 has just turned into a part of the skeletal formula there. And I've got this 1, 2, 3 of the propyl part, and then the C has become a CH2 and the N has become an NH2. And this sort of display of the skeletal formula here is set to catch you out, because you look at it and you think, there's some 2 hydrogens on there, and you don't balance the hydrogens here correctly. So just watch out, we've put 2 hydrogens on the C and 2 hydrogens on the N.